Good evening, everyone. I must say it's wonderful to see so many people here tonight in Melbourne, and welcome to tonight's event, Large-Scale Retaining Wall Design and Construction. Just to let you know, we had 300 people register for this event in the room, and we also have around 400 guests who are participating with this seminar via a live webinar. So it's great to see you all here. My name is Amanda Rogers and my role is Corporate Engagement Manager with Engineers Australia. And in keeping with tradition, we would like to, as we always do at Engineers Australia, acknowledge the traditional owners of the land. Tonight's event is being hosted with our industry partner, Austral Masonry. Austral Masonry is one of Australia's largest manufacturers of concrete masonry blocks, retaining walls, pavers and stone products. Austral's residential solutions can be seen on high-end architectural products and landscaping designs. While our commercial solutions include coloured and standard masonry blocks, large-scale segmental block retaining wall products, as well as a range of hard stand solutions such as commercial and permeable segmental block paving. Austral offer innovative solutions that provide structural integrity, excellent strength, durability, and they pride themselves on making beautiful products that last forever. The format of tonight is that we will hear from two speakers, and then those two speakers will be joined by a third speaker, Chris Lyons, Associate Geotechnical Engineer at Arup, who will join a panel discussion. And what I'd like to ask you to do, rather than we ask questions after each speaker, if you could sort of think through your questions, and then by the time we get to the panel, we'll have a facilitated panel discussion. Thank you also to everyone who submitted a question on registration, and we'll be also using those questions as part of the panel discussion. So, without further ado, I would like to introduce our first speaker, Dr. Chris Haberfield, Principal Geotechnical Engineer, Golders Associates. Chris is internationally recognised for his work on foundation structure, interaction and soft, weak-weathered rock. Chris brings high-level engineering skills, technical knowledge and practical experience developed through 20 years of research and teaching and 17 years as a consultant. Chris has been involved in projects such as the review and value engineering for Melbourne Metro stations, the new Gateway Bridge, tender design and north-south bypass tunnel in Brisbane. Chris has been awarded the 2005 Victor Milligan Award, the 2007 E.H. Davis Memorial Lecture, the 2009 Jack Morgan Awards, and the second Gregory Chabotery Lecture. Thank you and welcome, Chris.
Good evening. Amanda actually has got worse pronouncing that. It's Shebatarioff lecture. But she's the first time she announced it very well, but the last time was a bit... But we'll forgive her for that. If we work out how these go. All right. Tonight there's a wide-ranging audience, so I can't get into detail about retaining walls. I'm going to talk at high level, things to look out for, and so on, based on my experience and research into these types of applications. So I think anyone in Melbourne's familiar with this one. Can't really talk about it, but it's an interesting collapse of a retaining wall. I want to start off with a safety moment. As engineers, we deal with people's safety all the time. We don't talk enough about it. We need to talk more about it. We need to talk about safety in design. And when we design a retaining wall, we need to make sure we can construct it practically and safely. So there's some examples here. You would have seen the one on the right in the paper. The one on the left is a lift overrun pit All these are in rock. The one in the centre is in Brisbane. All unsupported excavations, all failed. No one was hurt, but the ramifications, obviously, of the failures are quite significant. And I'd like you to think about perhaps this one on the right. If it's an arrow work. You'll see down on the top figure, there's footings which have been cut. They've got reinforcement in them. So people have been fitting reinforcement in those. This is what I'm talking about, safety in design. Can we do things safely? So I have to sit here. I prefer to walk around, but I have to sit here because we've got the camera filming. So just forgive me if I get a little bit boring just sitting in the one spot. The retaining walls are a means of permanently steepening batters, often from something which is stable to something which is unstable. They create a void which things can fall into. Therefore, they form one of the riskiest things we do. Unlike tunnels, we don't give the retaining walls quite often the attention they need. With tunnels, we do a lot of work. It's an open excavation in the ground. We do a lot of work. There's a lot of engineering. Retaining walls, for some reason, we don't give it the same attention. And it's got the same risk of failure. When we design retaining walls, many engineers apply generic soil properties and formulas straight from the code, or straight from the codes, or straight from a textbook. They don't really think through whether they're applicable to the situation they are in. So I'm asking you to move away from that aspect and start thinking about the ground conditions you're doing the retaining wall for and what truly are the properties which affect the wall. When we do a retaining wall, it impacts on the groundwater. We have to think about temporary support and we have to think about long-term performance. If we don't do this, the retaining wall will not perform for the long term. Most retaining walls are put in to last a lifetime. How many actually last a lifetime? Most of them move, most of them are under design to some extent because we underestimate the ground. If we don't consider these things properly, we often choose the wrong type of retaining wall. And if we have, in doing so, we can often have significant oversights with respect to occupational health and safety, construction in a practical sense, stability, and what movements can be caused. One thing we must remember is a retaining wall is much more than a fascia. A retaining wall is not spraying shotcrete up against a wall and hoping it stays there. A retaining wall is a structure which has to support loads which we need to calculate. It's no good just relying on suction in the ground to hold the retaining wall up. If you're going to design a retaining wall, you need to think about what you are going to do to the ground. If you're going to excavate into a slope for a basement or dig down for a basement, you're going to unload the ground. The ground, when it unloads, has completely different properties than when it loads. Do you consider those? If we fill from an embankment, we're applying load to the ground. So it's a completely different stress path again. So we need to think about the properties which we're going to need to simulate the loading case, especially when we're putting embankments on soft materials. Both of these applications result in stable ground movements. Hopefully they're only stable ground movements, or they can result in failure, which are unstable ground movements, obviously. Both of these are considered failure. If you have too much ground movement or you have failure in an ultimate limit state sense, they are both failures of the retaining wall. It doesn't have to collapse. The other thing we have to remember is generally excavation can result in a change in the groundwater regime. And as I'll come to later, the groundwater is one of the most important aspects of everything we do. I probably wouldn't have a job if it wasn't for groundwater, because there would be, our engineering or our task would be so much simpler. And how often do we think about groundwater properly? So I really urge you to when we build a retaining wall, how will it impact on the surrounding ground? How will it impact on structures, roads, services, buildings and other assets? And can we build it safely? So let's just relook at how will the ground respond. You could get wall failure if you don't build it properly. You could get excessive settlement of both the wall and behind the wall. You can get excessive horizontal movement. You can change the groundwater regime. You could get possible piping and liquefaction. As you can see on this right-hand slide here, that's because the retaining wall did not go deep enough. It did not cut off the groundwater flow. The groundwater pressures were too high. They came in and they blew the base in. When that happens, you can lose the whole excavation, including all the roads and everything else around. We also have to think about if we're doing an excavation and putting retention system in the ground and it's got a higher groundwater table, if we lower that groundwater table, that can have ramifications for a long, long way. Especially if you've got an aquifer or something below your retention system, because you're lowering the groundwater pressure, that can affect for kilometres around. And we know that only too well in Melbourne. It's happened too many times. So most of you will know all this. So what do we need to consider? You obviously need to consider the height of the retained soil, the strength of the ground, the compressibility and stiffness of the ground. How many of you actually think about that? Because that controls movements. We need to think about the available space we've got to construct the wall. We need to think about the construction impacts and the temporary works to construct the wall. We need to think about the proximity of structures which are sensitive to movement, which are close to the retaining wall. And we need to think about the effect of groundwater. There's a lot of things to think about. In doing all this, we need to select the right type of retaining structure. First of all, it has to be practical and safe to build. It's got to suit the ground conditions, the geology and the groundwater, and it has to protect assets and life. Lots of things to think about. So, two very different uses. We've got embankments or fill, retaining walls which support those, and we've got retaining walls which support excavations. The engineering of embankments is relatively easy, unless you get on soft ground, then you've got to think about it. It's straightforward. The retaining walls, the supporting structure is erected as you lift the embankment up. So you're in control. You're always controlling the ground, the fill you're filling. The material you're supporting by the retaining wall is engineered. It's engineered fill. So it's got properties which are select for a start, which are reasonably consistent, and you're engineering the product. So that, and hopefully if you use the right material, the backfill will not change with time. Groundwater is usually not an issue because you're above the ground. Excavations, on the other hand, are much more risky. They're misunderstood and abused simply because too many people rely on suction to hold retaining walls up. I'll come back to this in a minute. The wall is supporting structure which places the ground. So in some stage you may need temporary support until you get that permanent retention structure in, and you need to think about what that temporary support will be. It's a relatively high-risk construction. Most of the retaining wall failures you will see are from excavation. The material you're supporting is natural. It's unengineered material. Quite often you don't even know what it is, because how often do you drill a borehole behind the retaining wall? It's usually within the site, not exterior to the site. So you might not even know what it is. You have to use geology to guess what that material is. Hopefully better than guess, you use logic. And the properties can change with time. The groundwater is often a major issue because we're digging down into the groundwater system, and you might need to consider such things as water tightness, drainage, discharge. Now it's getting to the stage where we used to do drain basements all the time. I'm not sure how long that's going to be allowed for. It's disappearing now, and we might have to have tank basements all the time, purely because of the discharge issues. And that is a whole different cost structure. and a whole different set of engineering problems. I want to take you back to your third year soil mechanics because I think quite a few of you have probably forgotten it. And I want to talk to you about earth pressures. Now, if I could introduce that red plate into the ground and I could put load cells on it so I could measure the pressure acting on the plate, and I was to compare that pressure acting on the plate with no disturbance with the vertical pressure, we call that ratio K0, or the pressure at rest. I'm going to come back to K0 in a minute. Where K0 sits is on the vertical axis, where you can see for zero lateral displacement on the right-hand figure. And there's two variations of how the pressure in the ground changes with displacement of that wall. So at zero displacement, or at rest, when the soil is at rest, that is the in situ horizontal stress, K0, at rest. If we now allow that plate to deform sideways, outwards into an excavation, but we're restraining it, so we're measuring the force which we need to restrain it as the soil fails. So the soil is doing the pushing. If we do that, we get a displacement and we move, the stress actually reduces and it goes down to a value called the active stress. But to mobilise that active stress only takes a very, very small displacement. As you demonstrated there, it plateaus off very, very quickly. If we go the other way and I now try and push the soil back, that's called the passive resistance. And I fail the soil by actually pushing the soil up against gravity. So the passive pressure I've got to apply to push the soil is much, much higher. But it also takes a lot higher displacement to get there. Now, so when you do an analysis of a retaining wall and you're relying on Ka, which mobilises very, very quickly, and Kp, which mobilises, might be 20 times more displacement to mobilise Kp, you need to think very carefully about what is happening. It's just not a comparison of Ka and Kp. You will get Ka movements, and that is the movement of the wall. It's very hard to stop unless you use an active retaining system, which I'll talk about in a minute. Both of these, Ka and Kp, are failure states. They represent failure of the ground. You can't have any stress lower or any stress higher. So your earth pressure is always going between those values. So let's have a little bit more look at K0, for instance. Now, why is K0 important, the pressure at rest? Because when I dig a hole, the K0 is what is relieved. And if you can, in a simplistic case, if you take K0 multiplied by the modulus of the material of the zone which is moving, you can work out how far the wall is going to move. If we don't know what K0 is, we can't work out displacements. K0 is not an engineering property. Okay, it depends on stress history, it depends on geometry, it depends on reactivity, and so on. So we have to try and make an estimate of it. We know it has to lie between Ka and Kp. And you're all thinking, oh yeah, but there's those equations relating phi and K0. They are for normally consolidated material. They are not for over-consolidated materials like we're generally dealing with in these conditions. We can estimate Ka and Kp reasonably accurately for soil. It's a bit difficult in rock. But when you estimate Ka, it depends on your strength parameters. Okay, mainly friction. How many of you actually go out and measure the friction of a soil? And when you do it, how do you do it? There's been so many cases I've seen people use quick undrain tests to measure the friction angle of a soil. Sorry, that is wrong. Doesn't work. You can't design retaining walls on quick undrain strength tests. Throw it out. If you've got a book which says that, throw it out. It is wrong. The other thing you've got to be very careful of, if you're starting to do consolidated triaxial tests or you make some estimate of strength, is the cohesion component. The cohesion component, even a small cohesion component, can reduce your active earth pressure to zero very quickly. 10 kPa cohesion for a soil which is, for a cut which is 2 metres depth, the Ka is about 0. So you are designing the retaining wall for no pressure. And then, of course, you put tension cracks in it and so on if you do the analysis correctly. Just be very careful about cohesion. It is not guaranteed. Most of the time it's probably apparent cohesion, which is suction. So you need to think about it very, very carefully when you're doing design. Remember, you're designing something which is going to last, say, 50 years. Are you certain the cohesion or the apparent cohesion you've got there is going to last 50 years? In certain rock materials where you don't have bedding and so on, yes, you can deal with it, and therefore some rock excavations will stand vertical. But what governs a rock excavation is the bedding and the structure, not the strength of the rock. So you need to look at the bedding and the structure. The other thing is that the design earth pressures you use for a retaining wall depend on the amount of movement of the retaining wall. If you're trying to restrict a retaining wall to 0 movement, you'll get very close to K0 stresses. If you allow the retaining wall to move, you're going to be close to Ka. If you apply very high active restraint through ground anchors or something to a retaining wall, you could push it up towards Kp. And I've seen some cases where people have been, I'm worried about ground movement in soft clay, so I'm going to put a value of, for a number, 12H as the earth pressure. 12H in a soft clay, you will fail the clay going back the other way. You will actually heave the structure next to you. So in being conservative, you're actually doing damage. So you need to get the horizontal stress about right. And it's a guess. It's an engineered guess, which is based on a lot of analysis and so on. Two different types of systems. I'm going to talk about passive systems and active systems. So passive system is basically where the retaining wall just sits there and reacts due to weight or some other system. These all develop their resistance through displacement. They will all have displacement equivalent to the loss of stress, in situ stress, from K0 to Ka. When we design them, we generally design them for stability only, and we generally design them to resist Ka. You have to be very careful about swelling soils. If you put a retaining wall in swelling soils, the swelling soils wets up, it's going to push the retaining wall. But again, the maximum force can only be up to the passive resistance or the swelling pressure. The swelling pressure is usually less than the passive resistance. You should not use such structures when you are close to sensitive you should not use such retaining walls when you're close to sensitive structures, assets or building, because you will get movement and you can damage them. They are great for embankments, and because if you have an excavation, you require a temporary excavation. I'm going to come back to this in a minute. So examples of gravity walls are shown here, the reinforced earth type walls and so on, gabions, crib walls and so on. Another type of passive system is your soil nail and your rock bolted walls. What are they doing? They're just basically stitching the front part of the excavation together to form a gravity block. So it's, even though you do different design methods and that is the basic mechanism. So you have to still design the soil nails to take the right loads and so on, but it's basically a gravity wall system. So it's going to suffer the same displacement. Gravity walls you know how to design. You've basically got that block, and this is very schematic, as someone picked me up on the other night. You've got an active earth pressure. You've basically got base friction, which is generated by the weight of the retaining wall, and you have to resist sliding, overturning, bearing capacity, structural capacity of the wall. And in doing so, you probably, as a rule of thumb, need the width on the base of the retaining wall of 50 to 60% of the height. You can reduce that down, but you have to design it accordingly. So if you see a really skinny wall, and it's a retaining wall, a gravity retaining wall, you need to investigate it further. And quite often the global stability is completely ignored. you need to do a global stability check. Another passive system is the cantilever, non-embedded cantilever walls, and these you can use where displacements, again, are not of concern, because you basically have to excavate before you put the wall in. When we go to embedded systems, you put the wall in before you excavate. But I want to question something. If you look very carefully at the photograph on the left-hand side, you'll see a person, a worker, between that cantilever wall and the excavation. I question the safety of that. And it's time we stamp that type of thing out. Also, there's a house immediately next to that 2 metre cut. That house would have moved. If that was your house, would you be happy with it? I wouldn't be. So let's stop doing that type of thing. Provide the right type of retaining wall for the right type of position. Embedded cantilever walls is the next system. We put these in before we do the excavation, and then you can excavate down. Obviously, these are full depth. So there's some shown here is some sheet pile walls. You've got a soldier pile wall where you've got piles at spacing, and then you've got shotcrete lagging, which you put in as you go down, but the piles are put in first, and they provide the main support. And you've got, as you go into more permeable ground conditions with high groundwater tables, you start talking about secant piles, but the depth to which you can install secant piles depends on the piling method, depends on the ground, depends on what finish you want, and so on, so you need to consider it carefully. And then you've got the diaphragm wall, which is probably the best type of wall, but the most expensive type of wall for permeable ground conditions. There are other methods you can use to get the piles in, so you can approach something like a secant pile wall, but I don't have time to go into tonight. The whole idea of these walls is you put them in before you excavate, you then excavate, so you're providing protection to the workers, and you provide some protection against movement to the services and structures behind, and you have to design for it. Because these move a fair bit, they're quite flexible, the pressures are generally close to Ka. A cantilever wall basically behaves like this. This is a very simplistic diagram. You have the active earth pressure, you will usually provide drainage behind the wall. You have a depth of embedment which is usually greater than the retained height, unless you're going into rock or something different, or something stronger and stiffer. And you have a passive earth pressure. But again, on the passive earth pressure side, remember about possibilities of excavation for services or whatever is going to happen on that side, which you need to consider. So you need to consider that very carefully. Then we move into a whole new system of retaining walls, active retaining walls, where we actually are trying to stop the retaining wall from moving. So we do this by using props or anchors, generally. And we do this by, again, we insert the retaining wall into the ground before you excavate, and then as you excavate down, you either put the prop in or you post-tension anchors. The stability and movement are both important, and you have to design these to limit ground movement. You need to do finite element analysis of these, and you cannot use the AS 4678, the Earth Retaining Structures Code. It is not applicable to these walls. You cannot use limit state design for these walls. You have to do your best estimate of the ground properties, and out of that get working stresses, working reactions in the piles and so on, and then factor those. There are some very good publications from Syria which deal with this type of thing, but they are all limit state. So just be aware that you should not be factoring down properties or factoring up weights or earth pressures or anything else for when you're doing embedded active retaining walls. It doesn't work. You'll get completely the wrong answer. The earth pressures you get from these are much higher because you're getting the anchor and you're pulling it back. And so the earth pressure distribution is very complex, and that's why you need the finite element analysis to not only do the stability, but also to do the displacements, because that's why you're doing it. You're putting these walls in to stop displacement. And this is much the same type of thing. You still consider the same type of thing. And don't be fooled just because you go and do a finite element analysis. You still need to check individual pile capacity if you're on a soldier pile wall, that the toe doesn't kick out or things like that. You still need to check those things. Just don't believe everything the finite element analysis gives you. There are other aspects you need to check. One of the things you need to check is the bearing capacity, because you've got anchor forces which are inclined and they're pulling the pile down. And I have seen retaining walls fail because they've been pulled into the ground by the anchor forces, they haven't had enough bearing capacity, and that causes the wall to move out. You've also got to think very carefully about the connection of the anchors to the wall, because if that connection can move, the wall will move out. You need to think about every aspect. Don't let the little details go past without investigating. We are generally very bad in Australia with respect to anchors. Okay, I personally don't think we put them in properly. We don't test them properly. We don't do our QA properly. The most important aspect of this system is the anchors. We need to do better. So as the structural engineers out there who are doing the drawings and that, there are very good recommendations within the earth retaining structures about anchors and that. Enforce them. Make the QA be done. Make the testing be done. Now I put this up because it gives us a comparison of the stiffness or what displacement you get from various types of walls. And this is for a stiff clay. And what you see on the vertical axis is first the horizontal displacement as a percentage of the wall height, and then the settlement as the percentage of the wall height. And along the horizontal axis you've got distance from the wall. So if we've got a 10 metre deep excavation, with an active system, you should expect in a stiff clay to get about 15 up to 15 millimetres of movement. You can get less as the clay gets stiffer and goes into rock, but equally well, if the bedding is in the wrong direction, you can get movements down to 15 millimetres. These are for well-designed walls. As you get less stiff and you come through the passive systems and the passive non-embedded systems, the displacements get significantly more. And this is why passive systems should only be used in greenfield sites, away from where things can be affected. The same thing about distance from the wall. I mean, note that it cuts off at 4 times the height. So for a 10 metre, that's 40 metres away. Now that doesn't mean the displacements out to that far are critical. It just means it can affect that far. So again, you need a lot of room as you go further down, come down to the bottom right of those graphs. Now water, I called the elephant in the room. No one wants to talk about it because it's always a problem. I can do a whole new talk on water, but I don't have the time. So rather than treating it at a cursory level, I'm really not going to treat it at all. All I'm going to say is no water, no worries. It's a saying from a colleague of mine from a few years back, Jack Morgan, and it's basically true. If we don't have water, we don't have problems with retaining walls. Water impacts on everything: the stability, the wall pressures, the soil strengths, the wall movements, the performance of the anchors. If you've got anchors in sand and you get a groundwater level rise because of, say, a broken water main nearby or whatever, you halve the strength of the anchor, and therefore the wall moves out. Do you consider that in design? If you're doing a retaining wall next to a 100-year-old water main, do you think about the possibility that water main could fail? And should we? Should we consider it serviceability state or ultimate limit state? Things to think about. Common solutions are to provide adequate drainage to get rid of the water. How long does that drainage last? How you design for it? Do you need to provide a system to clean it out? When you've got a clay material, not much water is going to come through. It's more a pressure relief situation. When you've got a sand and flowing water, you need to tank it because you can't deal with the water coming through. When you've got intermediate situations, like in weathered fractured rock and you've got water coming along seams, you might have a reasonable amount of water inflow, so you might have to have some method of maintaining your drainage structure. What about reactive clays? How many people do retaining walls and reactive clays put a gravel backfill behind it to act as drainage? Mind you, you're not going to get any water out of the reactive clay because it's such high plasticity it's going to hold it. All you're going to do is introduce water into the ground from the surface, and that's going to cause problems to your retaining wall. So if you're going to do that, you need to seal the top so water can't get in. I've seen houses blown apart by it because of water getting in. So in summary, retentions of fill embankments, well suited to passive systems because they're generally away from things. We need to be wary of bearing capacity problems, especially in soft clay. If you put a toe of an embankment next to a service which is in soft clay, you can very easily break that service. They're generally got stable lateral movements, but they're reasonably high. But they're not usually a concern unless you're close to an existing structure. You must use appropriate backfill materials for the application of the wall, and be aware that you can undercompact it or overcompact it, and they can have ramifications on the behaviour of the wall. You don't want to be jacking your wall out because you're compacting the hell out of it, or you don't want to be overloading straps in a reinforced wall because you're compacting it too hard and you overstress your straps. So you've got to be careful. Provide adequate drainage, both surface and subsurface. Bearing capacity, Selma already talked about. And don't forget global stability. Just also be aware the number of times as geotechnical engineers we're asked to do a wide road, a road widening or a railway access widening, and we're cutting into a slope. And when you look at the stability of the slope's only got a factor of safety, if we want to use that term, maybe 1.2. And then they asked you to guarantee that the retaining structure has a factor of safety 1.5. How in the hell can you do that if the whole slope has only got a factor of safety 1.2? So you need to be aware of that, because if the whole slope fails, it's going to take your retaining wall with you. For excavations, gravity walls, non-embedded cantilever walls, tilt-up panels, they all require bulk excavation prior to the work. Because you do that, you're going to get potentially unacceptable lateral movements and settlements within the zone of influence. So they are not suited in urban areas where we've got lots of assets and that around. The temporary batters are abused. These are general recommendations which most geotechs will put in their reports with respect to batters. 1V to 2H in sand, simply because sand will not stand up any steeper. 1V to 1H in clay, we're relying on suction in the short term for the clay to stand up at that angle. Over a long term, you will get failures in that. Greater than 1V and 1H in rock. Be very careful about rock from those first examples I showed you. You need to understand what the bedding's doing. We've had some classic examples in Melbourne where there's been bedding at 20 to 25 degrees, but the friction angle on that bedding has been 10 degrees and the rock has failed. So don't think that flat bedding, 20 to 25 degrees, is necessarily safe. You need to think about it. At these angles, some slumping should be expected, and you can deal with it as part of the construction. As we get steeper, your probability of failure is going to go up. Occupational health and safety is important. We're only allowed to stand next to a 1.5 metre deep cut, vertical cut. That's what the Occupational Health and Safety Act says. So how in the hell are you going to build a lot of these retaining walls, which are 10 metres high, with very steep batters? You need to think about it. So my plea is when you're doing retaining walls, understand the setting you're in, the geological setting, the hydrological setting, and the urban setting. They're all important. Protect the existing assets at risk. Always check to see what assets are there. You might often not be told. Choose the correct type of retaining wall and apply prudent engineering. There are a lot of cowboys out there who are willing to take shortcuts. We don't need to be part of those. And I would actually encourage you not to be one of those. I know we get pressures on us to steepen up batters and so on, but we need to think about safety. It only takes one batter out of 100 to fail and hurt somebody, and you will never ever design a steep batter again, and you'll be in deep trouble. Excavations and retentions are a risky business. They need to be given due attention. It's not something you give your junior engineers and walk away. You need to have a review of it. Let's not do any of this at the bottom right-hand corner. The building on the top, which you would have all seen on the web, was failed because of a 4.6 metre unsupported excavation. Thank you.
Thank you, Chris. I would now like to welcome our second speaker for this evening, Brad Irvine, who is the Director of Retaining Solutions Design Construct. Brad studied civil engineering at the University of New South Wales, then postgrad Masters of Engineering Science, majoring in geotechnical engineering with major thesis entitled Reinforced Earth Embankment and Foundation Interaction. Brad has worked for the Reinforced Earth Company for a period of over 4 years, followed by Macquarie Pty Limited for a further 5 years. He spent a small period working for Tenkate Nickel in Australia, then started and is still operating Retaining Solutions Design Construct for the last 15 years. During Brad's career to date, he has gained valuable experience in geotechnical and structural design of gravity, segmental walls, and reinforced soil structures for both commercial, highway and mining sectors, utilising both AS 4678 and RMS R57 and R58 specifications. No matter what type of retaining wall there is, they all have their own inherent characteristics and specific application. Please join me in welcoming Brad. Thank you.
Thanks again for the opportunity to speak tonight. Tonight was more probably a reflection of the experience I've had over the last 15 years. I've been exposed to a lot of different types of products are in the marketplace. We not only construct reinforced earth walls, but also get involved in design and construction. So one of the biggest things we have as a challenge doing design and construct is that element of where you are taking on the responsibility and the need to get more involved in terms of the geotechnical engineers familiar with the sites. So the structural engineers are talking and communicating with the geotechnical engineers of the type of wall you are trying to design, depending on the application you've got. So the photo up there just shows you a few different photos of the types of applications we're talking about. So the one on the far left is a mining structure, heavily loaded structure. Typically you're familiar with reinforced earth panel walls in that application, to a magnet stone wall there on the right. In the middle is a traditional keystone frictional connection system. The bottom left is a positive connection system supporting a railway embankment. And there's a hybrid system there, which basically shows a combination of using gabions and using keystone as a terraced arrangement to soften up the aesthetic appeal. So what I'm going to be covering tonight is essentially applications within the marketplace. There's a number of products. It is becoming more familiar with these products and how they should be used depending on the application, what the actual walls are sitting on and what they're retaining, most importantly what loads are being applied to that structure over the life of it. Important considerations we'll go through from design through to construction, backfilling, processes to look out for, some case issues in terms of industrial development, a business park and a development project, and some design construct references I've come across in my experiences which may be useful to the audience, and a closing summary. So first application is where you're looking at true and pole bridge abutments. So we're talking about heavy structures, large structures can vary from 2 to 30 metres high. Typically you will see panels used in this application. There are other types of structures. Most importantly, or products should I say, you are getting loads from 20 to 200 kPa applied on the top of these structures. So crash barriers, wheel stops, quite heavy impact loads. You are looking for more of an extensible reinforcement in this application. You need to look at the combination of that fascia with that soil reinforcement. So typically an extensive reinforcement, what are we talking about here? We're talking about saw reinforcement, which is typically strained to less than 1% under the serviceability tensile force. So you need a high facing in terms of the saw reinforcement capacity as a fascia, how that reinforcement connects to the facing and how that will perform under heavy loads and sustained loads. In other words, it's a positive connection system to that fascia. Creep of the reinforcement is important in terms of, again, those post-construction creep strains. A lot of these structures move during construction, regardless of whether it's a steel reinforcement or a geosynthetic reinforcement, they do move. And particularly with regards to tolerances, differential settlement, again, important things that need to be looked at. Road widenings, car park approach ramps up to bridges, again, different codes will dictate the type of system you can use in this application. Loadings can be up from 5 kPa up to 40 kPa. There may be crash barriers on top. They can be tied into slab arrangements, taking into account the horizontal force that may be imposed at the top of the wall. Important to look at. Extensible reinforcement typically can be used in this application, from my experience. So again, now we're talking about soil reinforcement, which is going to be strained to greater than 1% under the serviceability tensile force. There are a number of different types of different facings in the system. You can see there's some vertica, there's Allen block, there's keystone down the bottom left. There's different types of saw reinforcement. Again, as the engineer, you need to make yourself aware of the types of reinforcement that are in the marketplace and how they perform over the life in terms of temperature effects on the reinforcement, depends on the polymer, and also the types of materials you're placing and how that affects that reinforcement long term. And magnum stone down the bottom right there in terms of a frictional connection. We now move into those similar applications, but now we're getting up to walls higher in terms of up to the 15 metre mark. You're now starting to look at how the actual wall perform in terms of connection strengths. So then in this application, you will get loads up to 5 kPa up to 120 kPa. You look at pad loads that are coming close to these walls. So we're now running out of room on a lot of sites where they want to push buildings closer to walls. So you need to think about how the facing and the reinforcement will behave in terms of long term and how those loads will affect the fascia as well as loads imposed on the foundation and the wall itself. So creep strain is important. There's some different photos there. It shows you bottom left there's a Keystone TW3 system. Uses a polymeric connector which is actually recessed into the top of the block. Provides a positive connection to the reinforcement to the facing. So it shows you the photo there. There's key steel down the bottom, which is basically a keystone block with a steel ladder reinforcement. Again, same requirements you would have to apply to, we'll go through in terms of durability of that reinforcement over the life of the wall. Top right, there's an Anchor Landmark product. Again, positive connection system. It's got a lock bar within the recess of the block. Essentially locks the polyester geogrid in that recess. So you've got a positive connection. Again, there's a lot of testing which goes into these products, how they perform under creep and sustained loading over time. There's a photo down the bottom which shows you, again, the reinforcement laid out in relation to the blocks. This particular slide just wanted to highlight there are a lot of different systems out there in the marketplace. Every geosynthetic, every block system has a unique connection strength curve. You see there's a variety of different pictures there, from keystone to magnum stone to a gabion wall to a keystone TW3 wall, which has got a positive connection. You'll see there's unique strength curves. There's a lot of different geogrids out there, so you need to ask the right information from those suppliers. Do they have those connection strength curves? So when you are looking at alternative systems that come across your desk, you need to make sure that they are equivalent, not in terms of just the long-term design strength of the reinforcement, but also how that reinforcement will behave with that facing over time. So that connection strength is particularly important. So you need to look into the supplier data sheets to make sure you've got the right information, how it behaves with that facing. Gravity walls, Chris has touched on conventional gravity walls. Again, they're quite familiar with the traditional methods, so crib walls, gabion walls, masonry no-fines concrete walls. There's mass block, lock block, traditional reinforced concrete blockwork walls. New systems we will touch on tonight is magnum stone with extenders. We'll talk about the benefits of that in terms of cost savings, potential cost savings. Stone strong, post and panel walls, traditional steel I-beams or columns with concrete panels in between, satisfying durability requirements, which is the new inception of that type of product into that application. You need to be very careful though on the subgrade conditions in which you're designing and building those types of walls. So again, it shows you the traditional gravity wall using concrete or a concrete crib wall, and also using gravity walls in terms of gabions. They need to be laced together the right way and designed as a gravity structure, not as a skin. It's not a fascia. Cut situation, again using mass blocks, another system out in the marketplace. It's typically a no-fines concrete unit. There are lifters in there. They create a gravity wall by including a mechanical connection between the no fines and the fascia by galvanised rods which are mechanically attached to the magnum stone, to the mass block. Again, it creates an effective width as a gravity wall. No fines concrete walls, it's quite a cost-effective or new solution. Again, we've done walls up to 2 metres high using Keystone and no fines concrete. There are specifications for the placement and the right placement of that material as you're coming up with construction. Above 2 metres high, we've also decided to put in a reinforcement to provide a connection between the no fines and the facing. So important that will also last long term. So we've used HDPE and high density polyethylene in that particular application because of its pH limits. It's actually tolerable to high pHs associated with concrete. Cut and fill situations, you have the opportunity to use a gravity wall, then phase that into a reinforced saw wall in the same structure. If it's a gabion wall, as I said before, you can use different types of reinforcement between the gabions. That shows you a Paralink product, again a polyester reinforcement. Again, you need to get the data to assess that as a solution. So you're not looking purely just as a global stability or sliding and overturning of that mass, but also internal stability, or what they call a local equilibrium method, how that performs under vertical load in terms of pull out of that reinforcement. Magnum stone, another product, a different fascia, again, same principles need to be looked at. So you can use it as a gravity wall, also uses a frictional connection where the reinforcement just sits in between the blocks and relies on a gravel interlock to hold that in at a vertical load, or a positive connection system there will actually go through the cores of the block and come back and extend back into the fill. They've also used it with anchors and other different types of reinforcement are attached to a cut. Again, not familiar with that application, but again, you need to look at how that will perform in relation to the wall. Gravity walls, in terms of using extenders, you're looking at a concrete crib wall or a gabion wall using extenders. Shows you there you can use a 2 foot or 4 foot, creates a series of silos. You're filling up with aggregate. The cost savings versus that in relation to using no fines concrete, there's a big cost difference here. So it needs to be assessed. Again, stability of cuts, you can see that cut's quite steep. You need to be very careful about the geotechnical considerations in terms of temporary support and the risk you've got in relation to the workers. Stone Strong, another large block system. Same thing, can be used as a gravity wall. Also be used as a reinforced saw wall. Again, you need to get the same information regarding the saw reinforced and the way it's connected to that type of fascia. And sleeper walls, engineered by application. Again, you need to be very careful on the ground support you've got with these types of walls. Typically up to that 1 to 4 metre high mark is what we've had experience with. Past that point, you need to be very careful of the spacing of the posts, capacity of the posts, and also the actual structural capacity of the panels you're putting in, or individual sleepers. So in terms of considerations, Chris touched on most important is geotechnical. You need that geotechnical information to make sure your design is going to be able to also work short term and long term. So there's design loads, information, performance criteria, the aesthetics again. Sometimes the application and the site you've got may dictate the type of solution you're going to use for that application. Foundation preparation, paramount to the performance of the wall. We'll go through backfill placement and compaction, how important it is in relation to the movements of that wall as you come up, and also performance. Saw reinforcement, how it should be laid level and compacted. Drainage provisions, and under the standards there are a few different options. Again, you need to be very careful in regards to reactive soils. You don't want to encourage water to come into the structure. Monitoring, times and most importantly, maintenance. So just briefly touching on, again, you've got to look at the geometry of the wall. What's above the wall in terms of batters, what's below the wall. Your foundation capacity in terms of settlement and bearing capacity. Dead and live loads, if you've got heavy loads in the face, you need to think about, do you need a positive connection system? Do you need extensible reinforcement? These are things that need to be looked at in terms of that performance criteria for that application. So it shows you that in terms of strip loads and those sort of things, they need to be looked at in relation to the facing if it's within the active zone. Ultimate limit states, we're looking at external stability, so bearing capacity, sliding, overall global stability. Serviceability limit state, settlement of the structure in relation to that foundation which you're placing that retaining structure on. Internal stability, we're looking at post-construction strain and the reinforcement. You need to be very careful regarding using fine-grained soils, particularly when you're reworking them. Foundation preparation, paramount to the performance of any wall. So you need to look at differential settlement in terms of the capacity for those imposed loads. Again, soft spots need to be replaced with engineered fill and compacted. You need to make sure how that's going to affect in terms of water ingress and how you can actually place that foundation to meet that bearing capacity requirement. that shows you a photo there, and that was actually an application where there was a 16 metre high reinforced earth wall in a mining application. We were lucky enough to find an artesian spring coming up underneath that area. So again, we had to dig down 4 metres and replace that whole area with a raft. So there was constantly water coming in there. So the wet and dry strengths of that material we put in that hole was critical in terms of the way it was going to meet a bearing capacity and also settlement of that wall. Again, every application will dictate a certain treatment. Backfill, there's a variety of different types of backfill you can use. Our experience is the backfill material that you do use within that reinforced fill zone needs to be a granular and non-expansive material, and most importantly, it's actually got to meet the requirements the engineer's designed for. So you don't want to design optimistic friction angle, you want to have backup in terms of testing. If you're looking at peak or constant volume friction angles, there needs to be testing, so there's ITPs and there's close out of different hole points from the design process through the construction process. And most importantly, backfill is the key to the performance of these walls. You use poor quality material, you probably have excessive movements, and you get poor performance of the wall. Again, it needs to be durable. You need to assess that material in terms of how it's going to affect the long-term performance of that reinforcement in terms of strength and also damage on that reinforcement as you're building the wall. There's a cross there in that photo, it's basically saying that the experience in the past, you do not use shale or clay stones or mudstone, because as soon as you recompact it and wet it up, you're basically lowering the strength of the material again. So stay away from those types of materials. Backfill in terms of considerations, in terms of what physical and electrochemical criteria, there are specific requirements whether you're using a steel and extensible reinforcement or a geosynthetic extensible. Again, sizing the material, there's different guidelines there for 150mm minus down for a steel reinforcement to a geosynthetic 75mm. You need to be also very careful of your placement method, typically a third maximum size of the maximum lift thickness. So typically materials you'll be using 50mm to 75mm as a grading size down. There's requirements in terms of pH. Again, different types of reinforcement are affected by pH. So steel is typically 5 to 10, polyester 4 to 9, and HDPE has a wider range, so it's a bit more tolerable to ranging soil conditions. And steel reinforcement, again, chlorides, sulfates, all those other tests need to be checked in terms of resistivity as well, how that's going to affect the degradation of that steel over that design life. There's also a requirement you can look at in terms of what you're placing behind the reinforced fill zone and above in terms of your batters. So spreading and compaction, so regardless of whether you're using a panel wall or a segmental wall, it's particularly important your compaction processes are closely monitored during construction. So also the moisture content of the material. Are you placing it dry of optimum? You're going to be very careful how that moisture content will affect the performance as you put those layers out. It will affect the integrity of the structure, your processes. So direction parallel to the wall, not perpendicular to the wall, you'll end up pushing out the reinforcement and cause excessive deformation on the facing. So again, stage construction, you want to avoid damage. You need to make sure whatever the process you've got, the rubber tight equipment, regardless of whether it's steel or geosynthetic, you need a layer of fill over the material as you're spreading and compacting. Again, you want to avoid excessive deformations and displacements. This is a probably important photo we've taken in relation to a wall we've built and also segmental walls. So we've got two different types of systems, both segmental units. One's are bigger than the other one. One's a positive connection with the steel reinforcement. The other one can be used with different types of geosynthetics, using a positive connector and also frictional. So again, there's different zones. So within 1.5 metres, typically called a hand compaction zone. Again, you're using equipment less than a tonne. So jumping jacks, compaction equipment. Again, control methods to get your target density within 1.5 metres of the wall. Past 1.5 metres of the wall, you can use heavier equipment. Again, control processes. When you move into a segmental wall, we'll go through the system, whether it's a frictional or a mechanical connection on a segmental wall. Again, you need to compact the gravel within the cores of those units, the first 300, extending back to 1.5 metres. Again, it's critical in terms of how the reinforcement creates that gravel interlock which holds that reinforcement if you're looking at a frictional system. So it shows there an 80 kilo plate. Again, you will see the material drop down. Once you run a 80 kilo plate along the back of the blocks, you'll see the aggregate sink down. That's what creates a gravel interlock and how they test these different types of fascias with the geosynthetic between there. That shows you a snapshot. A lot of this isn't talked about, but everyone says there's connection strength curves in these software programs. The way they test that in the laboratory, that shows you. They actually hand compact the material within the voids, To fill all the voids, they put the geosynthetic in between the two blocks, put another block on top, fill that again, then apply a vertical load. Then they, under vertical load, and they also measure the deformation of the geosynthetic at the back of the unit, so you'll create a strength curve under a peak in the serviceability criteria in terms of movement. So it's particularly important when you're building in the field as designers to make sure when they're building the walls, they're creating the same scenario as what you actually designed. So compaction of that gravel material as you come up, not allowing people to multi-rack, which is a fast way of building a wall, and you don't want to put scaffolding in the front of these types of walls. Why I've come across this is probably important thing to drill in as engineers. These are some of the practices that are occurring. So they'll multi-rack the walls, obviously to avoid putting a scaffold up to build it faster. Are we actually constructing it the way it's been designed? No, you're not. So multi-racking, you see the problems there. The main key, obviously, you're not getting adequate compaction within the cores. So that gravel interlock we've talked about, when you're relying on just purely friction, you're relying on overburden of those blocks, that's what creates a gravel interlock. So that's not compacted. You are not resembling anywhere near to what your design strength curve is. So poor compaction again within that zone. You'll see down the bottom there, the actual geosynthetic drops down and goes up. The amount of additional load and stress you're putting in that reinforcement at the connection, it's regardless of whether you've got a steel reinforcement or a polyester reinforcement or HDP. You need to make sure those processes are backfilled up to the top of that block and you're filled up in each consecutive lift. So these are things to look out for that don't happen on site. You want to make sure that it's actually being constructed the way you've designed it if you are taking responsibility for the design. The last thing you want is cracks at the back of the pavements there, purely where you haven't been doing the hand compaction or consolidation zone the right way. So it shows you there's some photos there of saw reinforcement, again placement, and then to level with the unit, whether it's a block unit or a panel unit. You have to get the material up to the actual connection where a steel strip actually connects to a panel. Same thing, you're putting additional load on the connection. But you've got a positive connection. So if you don't get that gravel interlock and compaction with a segmental unit, you're dramatically losing your connection strength, and you essentially will be relying on the connector to provide that strength. So it's very important that gravel is filled up in controlled lifts as you're doing the unit placement of the blocks. So typically it's a maximum of 3 courses, or twice the depth of the unit as a rule of thumb. Before you need to put 2 lifts, a lift to fill in, gravel, lift to fill, gravel, compact it up to level. You may need to top it up to make sure it's level. So you can actually install scaffold external to these walls. There are ways to do it to avoid that scenario, but again, it shows your photos there the importance of reinforcement laid. Compaction is critical to the way these reinforced saw walls perform. Drainage, Chris, it's paramount. Again, whether it's a dry land structure or a water application, there are different solutions in the Australian standard. It depends on the amount of water ingress you've got coming in. Consult the geotechnical engineer on site who's done the report. Assess where the water's coming from. That's going to affect the long-term performance of the wall. So they look at you can see in the middle there, a gravel chimney drain, full height, 100% coverage they would call it. Typically a gravel trench with geotextile both sides. You may wish to do a heel drain at the back of the wall and incorporate a geocomposite product from one of the suppliers. Again, you need to look at what sort of flow rate you're getting out of that and what it's going to capture to make sure that water gets away from the structure. Make sure water doesn't pond to the bottom and will create a loss of strength in the foundation. Monitoring during construction, most important thing with any type of segmental wall. A lot of the smaller units will have their own, you'll see pins, it's spacing alignment tool. You still need to gravel fill them and compact and use a string line. But it shows you there are a few examples with regards to whether it's a panel wall or a segmental wall. Panel walls move. So every lift to fill you put in, that panel wall will move in relation to the next one. So you need to monitor as you come up. You do a 250 lift, it'll move 0.1%. They will move anywhere between 10 to 20 mil over that 2 metre height for a panel wall. Segmental walls, again, for a 150 layback, you may have, that's 4 mil per course, they're typically 200 mil high. Again, you need to make sure that they're running a string line. Pins are one thing. Once you actually put the pins in, you locate the blocks on there, you still need to run a string line and keep it level with the wall as you come up. Again, control processes. Magnum Stone has a secure lug system on the bottom of it. You still need to make sure that the wall is brought up line and level as you come up. So again, supervision, you may also put survey for reflectors on the front of the wall as you come up. Tolerances, a lot of specifications will dictate tolerance. Be actually a good idea as a structural engineer or geotechnical engineer to put actually what tolerance you'd like to achieve. So things are monitored during construction to avoid problems later on. plus or minus 50 mil for the reinforcement coming off, the connection where that reinforcement connects to the facing. Design inclination of the face. Typically 1 to 2 degrees you've got in terms of movement. Another way of looking at it is a plus or minus 50 mil of that design position. So again, monitoring hole points during construction is critical to the performance of these walls. Flatness of the wall, one check is a plus or minus 20 mil on a 4.5 metre straight edge. Typically more for panel walls where you'll see shouldering. So again, if you monitor it tightly during construction, you'll avoid those problems long term. And RLs in terms of finishing levels, again, there are different tolerances in different specifications. Maintenance, again, regular program. A lot of the problems we've seen with the retaining walls that we've built, maintenance long term, is how the actual batters are finished around walls, and there's been protection on the batters, so to stop water coming down the back and actually creating a problem. So spill through batters at the end of walls, have you thought about that? Because when you get rainfalls, you get scarring down the back of the walls, dish drains, all these types of things actually prevent maintenance long term. But when you are looking at walls that has actually suffered some distortion or displacement, you'll get panels out of whack, you'll get damage to facing, but again, drainage, that's the main key thing with regards to finishing these walls off. It's the last 10% of effort in terms of sealing that structure will affect the performance. There's a few case studies here we'll go through in terms of what was used in a few industrial developments. One particular first application is a saw nail wall, which was originally specified. Again, showed you a noise wall on top that had to be constructed as a top-down construction. So it's fairly important in terms of the design loadings on that type of application. There was also a reinforced saw wall, which we use a frictional connection in, typical pavement up to 4.5, 5 metres high. There was also a saw nail up to 13 metres high with a reinforced saw wall above. Now, this particular project, we looked at using the Keystone TW3 system. Again, the key to the success of this whole solution was the stability of that embankment. So rather than using a top-down construction, we proposed an equivalent gravity wall, which would have the strength not only to take the noise wall loadings, but also be able to cope with wall heights up to 13 metres high. And we're using, again, a good granular material. So the batters was the key to the success of this job in terms of opening up different sections and monitoring that cut as we went along. Was a bedrock. Again, the top couple of metres was exposed. Didn't require nailing, but monitoring by the geotechnical engineers was critical, opening up it in stages as we went along. The first wall, which shows this, was about 760 odd metres long, got up to about 7.8 metres high. We installed sleeves during construction within the reinforced fill zone. Again, we used a positive connection system in terms of looking at those wind loadings and how that would affect the top 2 metres of the wall. So AS4678 was used in terms of looking at internal, external stability. Global stability was checked in terms of compound failures through the wall and also outside the structure. Again, 1 in 16 layback, so they specified the same angles what they had for the saw nailing in terms of the shotcrete. Monitoring was done very closely with each successive lift. Surveyors were monitoring every 2 metres as we were coming up to make sure it was in design alignment. Speed of construction was also a consideration in this, and there was an abundance of sandstone in Sydney at the time, so it was a good solution in terms of what was presented. So that shows you there some photos of using that particular product. Again, a lot of the backfilling was done from the front of the wall. Shows you the noise wall completed at the bottom left there. Some noise wall posts were installed. Again, and sleeves were installed during construction. Compaction, very important around those sleeves, was about 2 metres off the rear face of the units. Another wall on that same site just shows you about 460 metres long. Wall heights vary from 1 up to 13 metres. Connection strength, positive connection system, paramount in that type of situation due to the wall heights and the loadings on the wall. Same checks were made as the previous wall we just discussed in terms of internal stability, external stability. Again, in this case, you'll see we used a step or a trapezoidal block because we were retaining a rock excavation. So to limit the amount of excavation, we're also controlled by boundaries at the back. So we work very closely with ATNL, which is one of the principal consultants, as well as PSM Geotechnical, to check not only the performance of the wall, but also the tolerances we had in terms of batters, opening up excavations, and the like. So that shows you there some photos. Again, rock batter. You need to be very careful of how steep the batter is going to be in relation to stability during construction. The main thing is safety of the workers. So it shows you there some photos. We used, in this case, a chimney drain at the back. So it was a 2 metre high gravel drain against the cut. And we used Megaflow at different orientations along the back cut to intercept the water that shows you there a photo of just the two walls. First one, you can see the dark grey. I don't have a laser pointer, but it shows you the extent of it. They're putting the batter above it. Second case study, again, it just shows you a terrace wall. In this case, we use a Gabion solution at the back. The main solution to look at here, the problem was the interface and the interaction between the two terraces and how that affected the lower gravity wall. So because that wall, the architect actually wanted the wall to be on a snake appearance along the whole length of the wall in relation to that road. So it was a softer appearance to the eye when you drove around the corner. Problem was, from a technical point of view, that terrace wall affected the Gabion gravity wall at the base, so we had to make sure how we would solve that problem. So in that case, we looked at using a geosynthetic solution in between the Gabions to create one coherent mass. Again, same checks were made: global stability, internal, sliding, drainage. Particularly important to make sure we captured the water at the back to make sure it got away from the structure. So it shows you there some photos of the geosynthetic laid out for the Gabion wall at the base, and the two keystone terrace walls were behind. So again, it was on a curve, not as fast as a traditional straight wall. Important that the reinforcements placed a certain way and the backfill spread and compacted as you come up to make sure that it's got coverage between each layer. And that shows you a completed photo just showing you the Gabion solution. Again, there was bioretention basins at the base of that Gabion wall. Global stability was a concern there. We also used that reinforcement to satisfy that criteria in relation to the batter at the back. And the last case study was just to show you the application of using Magnum stone with geosynthetic as a reinforced soil wall and also as a cut wall at the back as a gravity wall. Extenders weren't used here, but it just shows you there. Same processes with using a segmental wall, using keystone or panels. Reinforcements laid, again, gravel is actually filled within the cores, that's compacted, geogrids placed, another unit's put on top. Cut application at the back of the site. Walls varied up to about 4.5, 5 metres high. We used Magnum stone with no fines. Extenders weren't around at that point in time, but we used Tensar as a connection between the no fines and the fascia. Particularly important. Next time we'd obviously go look at the solution of using extenders purely to offset that cost of no fines concrete. Again, you'd look at, most important, what sort of material you're putting behind that gravity wall as you come up. And also it's free draining. Again, you may also utilise some cross drains to make sure that water does get out. And it's on a reinforced concrete foundation. Again, you must look at your bearing capacity to see what type of footing you're going to be using. Design and construct references. There's a number of the Australian standards. There's some other publications that are well worthwhile looking into the history of these types of walls so you understand the principles of design in relation to construction, the right things to look out for. The CMAA have also had 2 publications, and the RMS have got their own guidelines. The last publication on the right that just talks about the emphasis of these walls on low height walls, on batters and heavy surcharges. You need to be very careful looking at a gravity wall compared to a reinforced soil wall. And in closing, with all these walls, most important thing is geotechnical information. Doing design and construct, a lot of the risk has been shed onto the guys doing that component, so it's really important to make sure you have the right information geotechnically in terms of the type of wall you're going to build. There's a lot of different products out there you can use for these types of applications. You need to choose the right product. Sometimes your design requirements will dictate the type of product you are using. Identify the application in terms of the structure, the loads that are imposed on the wall. The geotechnical considerations will dictate type of wall, the dead and live loads, global stability, settlement and drainage is the most important things to look at with these types of walls. And once you've chosen that, then you may go back to the drawing boards. Your client may have dollar considerations to look at. So again, there's quite a few different points. So once you've addressed all those, hopefully you will come up with the right application and the right product to use. And thanks for your time.
Thank you, Brad. I'd now like to ask Chris and Brad to sort of take a seat on the chairs for the panel discussion. And just before I introduce Chris from Arup, just to let you know that we'll spend a few moments. We did take questions on registration, and we will use a couple of those to get the panel discussion going. We will then say goodbye to our webinar audience, and we will take some more questions from the floor. So I'd now like to introduce Chris Lyons to join us on the panel discussion. Chris is Associate Geotechnical Engineer at Arup, and he has 20 years' experience covering the geotechnical design of various types of deep and shallow foundations, ground improvement, retaining walls and slope stabilisation, working for both static and seismic loadings. Recently, projects include proof engineering for multiple reinforced earth walls up to 50 metres high, design of 23-metre deep fill embankments, and he's currently working in the design of deep station boxes, ground movement prediction and damage assessment for the Melbourne Metro project happening here in Victoria. So welcome to Chris. Thank you. And we might just start with Chris. So if you could just take a little bit of time now to think about your questions, but we will have a couple of questions that were submitted on registration. One of the most popular ones that we did receive, and I'd like to put to Chris, is can you comment on the value/benefits of CPT and dialometer-based geotechnical investigations?
Yeah. Obviously those types of tests give you much better information on the strength and the stiffness of soil profiles, and that kind of alludes to what Chris has talked about in terms of assessing the Ka and the KP parameters. So there's obvious benefits with it, but I think you've got to get the right scenarios. You know, if you're on a rock site, then you're not going to penetrate in, so you're going to get limited information. And you also probably want to have boreholes to kind of confirm what the ground conditions are associated with those tests. If you're in seismic zones, then they're great for assessing liquefaction studies, but again, in Melbourne, that's not such an issue, maybe in eastern Victoria. So, yeah, they're really good for improving soil models, but I think you've got to have the right situations for them.
Chris H., would you like to comment on this?
Dilatometers are actually quite useful, and I'm talking about the flat plate, Marchetti flat plate dilatometer. For getting an estimate of K0 in certain soils. It's probably the only instrument we have. The situation we have in Melbourne predominantly is with basements and so on is with rock stresses. There's been a lot of work done lately for Melbourne Metro which establishes, has helped define the rock stress profile around Melbourne, and it's a fair bit different than we originally thought it was. And so we need to consider that, and hopefully that information will come to light for other people not working in Melbourne Metro soon. But it needs to be very carefully considered. The CPT, of course, is a very useful tool, especially in soft clays and sand materials, and I would encourage its use. It's quite often a lot more benefit than a borehole.
Thank you. Another question that was submitted on registration is that I'd like to ask the panel to comment on where we as an industry are versus where we should be with respect to risk management maturity and the use of geotechnical baselines in contracts. And Chris Haberfield, you may want to start off with that.
Oh, dear me. Ask the question again, just so I get it right.
So to comment on where we are as an industry versus where we should be, maybe, with respect to risk management maturity and the use of geotechnical baselines in contracts.
Okay, geotechnical baseline, I mean, I'm not sure I'm answering the question but I'm going to say it anyway. We have a process here of design and construct, and I don't think it's working. We don't have the oversight that we should have, except in a few a few very large projects, and we've got builders and installers of various structures who are self-certifying. There's no engineer overseeing that other than who are working for that builder and so on. I don't think the system is working. We need to go back, I think, at least some way to having an engineer in charge of the project, an independent person, and I think we've got to start now. So while we do very good work in doing baseline geotechnical reports and so on like that, I just don't think we're fulfilling the Q&A and all the other procedures we need to. As an industry, we are letting ourselves down. I hope I answered that question.
Chris, do you want to comment on that?
Yeah, I think there's a lot of risk which is just imposed onto the contractors, which I think makes it hard for them to manage, and I think their clients potentially need to take on some more of that risk and have a bit of a sharing. And I think supporting Chris's comments there about sometimes with construction, I think there's cases with anchors and various types of solutions where they haven't necessarily been constructed correctly, and without proper levels of control or QA or things like that, then you can have failures or issues which can occur. And so I think we need to make sure that's kind of getting implemented. But it all adds cost to projects, and that's potentially where the industry is not quite at the optimum place.
Maybe for all of the panel, but in both presentations we talked about safety and the importance of the engineering profession and you as engineers for taking the lead. And we did have a lot of questions about safety. And one of the questions is, what are the typical factors of safety used for overturn instability in design of large retaining walls?
Well, for sliding 1.5 and overturning 2 are probably common numbers. But then, if you look at something like R57 or AS4678, for these types of walls, they use different approaches. So a factor of safety may not actually be compliant with Australian standards or the guidelines or recommendations. So there's numbers there, but they're not necessarily code compliant.
I think it's time we actually started moving away from factor of safety and talking about reliability and probability of failure. The factor of safety is completely dependent on the input parameters you put in, and everybody can make up most of the time we're making up the parameters. So the factor of safety, it works out. That's what you get. You get 1.5 or you get 1.3. You tweak the parameters a little bit, you get a different number. We need to start dealing with reliability and probability of failure. It's not that hard.
Brad, do you want to comment on that?
Yeah, I think it ties in with the design construct process, particularly you will get the influence where people are moving dirt around quickly, they want to get walls constructed quickly, and the process of tying this peer review back into these soil parameters and getting the right information is critical to what the other speakers have said. You can run a sensitivity analysis, but without the information you can't be able to tweak, you are getting the right answer, and that's where the limited geotechnical information that's out there. They may do an original geotech report for the site, may be very preliminary, but they will always say once you start actually moving dirt and opening up the ground, get that geotechnical engineer back to confirm those parameters, because that's basically what your design's based on. So if you can't do a sensitivity analysis, you're not going to be able to fine-tune where you actually lie in terms of the way that the wall is going to meet those requirements.
Thank you.
I want to make one other comment. We keep talking about factor of safety, and that's a limit equilibrium condition. We need to start thinking about deformations because they are critical.
Thank you for that. A question that we all have is what are some of the commonly overlooked factors affecting the suitability of a large-scale retaining wall at a particular site, which is quite a general question. But a lot of the feedback that we've had in this seminar over the last 3 events has been around that topic. So maybe Chris Lyon, if you'd like to just open up on that one.
Yeah, I think the internal design of these walls is well, there's systems in place which are quite stringent and quite robust, but I think it's probably a lot of the external things that go on. It's the settlement effects underneath the walls, the global stability that Chris was alluding to. I think what Brad was saying about some of the details around the walls, controlling water and that. And from my experience, we've had soft soils with a lot of sediment underneath these walls, and they're great, they can tolerate that. But for instance, if you were putting piles underneath the front of the wall to reinforce it, but you're getting settlement from behind, then you're inducing additional strains in the walls. And I think also compatibility, if you've got a piled bridge abutment with a reinforced earth wall sitting on soil, it's those strain compatibility things. So I think the wall design themselves, I think that's relatively robust. I think it's the effects, how it sits in the surrounding areas like settlement, which is the issue.
Just to add to that, I'll go back and half. Temporary works in constructing the walls, temporary batters, we abuse them. Quite often with embankments, we don't think about embankment spreading. We quite often will do a design just with an embankment load, a vertical load on the ground, and we don't think about the foundation, which is actually stopping that embankment from spreading. So we need to think about that as well.
Brad, do you want to comment on that?
No. Leave that for Chris.
Just with the interest of time, I'd like to thank our webinar audience this evening for being here online and so many of you to participate. Just to let you know, the recording, we will be sending it out again. We will send it to everyone who's either physically attended or registered for the webinar, so you can watch at your leisure and obviously share with your network. So maybe we'll have a round of applause for our webinar audience. Thank you.